and 20% immediately will be delivered to the kidney approximately. But intrarenal, you are definitely going to focus in on the kidney, but some of it will go back into circulation. So.
Got it. Do you think it's similar to the retrograde in terms of spreading to other, or is it?
No, I think it'll be more spreading. So I would say if I rank them, retrograde would be the least, medium would be the intrarenal, and artery would be the worst.
Okay, I got it. So so it sounds like retrograde is kind of has some advantages if you need to go locally, right?
Yeah.
Okay. Thank you. This is really helpful. This is our first interview, so.
Sure.
I'm still a little catching up to speed here. Okay, so great. Just as
I said, I am not aware of any papers so far. I'll be interested to know now, but of retrograde delivery. But it's definitely scientifically makes sense, I suppose. But I am not aware of any papers using retrograde approach. But I am interested now. So sorry, I didn't mean to interrupt.
So I mean, I'll tell you what I've seen. I mean, I've seen. Look, I don't want to name any names, but I've seen faculty at UPenn pushing this recently over the last few years, and they're basically publishing what you're saying off the top of your head, that you can reach the epithelial cells of the kidney. There's less spread to the other with the retrograde. They think it's clinically, considering we're talking about a one-time treatment, that could potentially slow down, fibrosis indefinitely, right? Stuff like that. I mean, I think I'm trying to gauge. So everything they published agrees with what you said. I think, and they're pushing it. I think that they're saying that it does better at getting to those cells than other routes of administration. And I mean, that what I'm trying to understand is which diseases, would it be clinically relevant, assuming you can deliver the gene you want and you can improve the cell type, right? I mean, what
kind of diseases?
Yeah, so what diseases would a patient sign up for that one-time treatment that's a cell therapy? Or a gene therapy,
virus with gene therapy, yeah.
AKI is. Yeah,
AKI would be easy one, but it depends on what kind of AKI. If you're obstructive AKI, how you can access depending where the obstruction is. AKI for sure. Any tubular diseases like polycystic kidney disease. Again, the thing with polycystic kidney disease, you're going to have to catch this very early. So that's the other problem, is diagnosing the patient early enough so that before the diseases started setting in to affect delivery of the virus. So that, of course, you could try retrograde. Like I said, you could probably reach the podocytes as well this way, theoretically. Any fibrotic diseases like diabetic nephropathy potentially. But again, diabetic nephropathy is just not tubular injury. Although people believe this tubular-centric view, it does affect the mesangium and other cells inside endothelium. So I don't think I would not see this as a mode of delivery for a diabetic nephropathy. Any of these systemic disease, lupus, all these ones, I wouldn't think just retrograde would work. But for anything tubule-based, potentially podocyte-based, you could deliver it retrograde. So tubular disease would be ATN, rejection, again, cell-mediated rejection. Cell-mediated rejection, it has many other components, but tubular cells are a major part of the target. The reason the focus on the tubules is for two reasons. One is most diseases do affect the tubules. Second is they make up the largest, tubular epithelial cells make up the largest part of the kidney in terms of mass. So the parenchyma itself is mostly made up of tubular epithelial cells, depending on whichever region. So the rest of the stuff, like blood cells, blood endothelial cells, and endothelium are a small part of the mass of the kidney. So I can see why they are using these retrograde approaches, because the tubular epithelium makes up most of the tissue of the kidney. So so you wanted some other specific things like
Doctor. Yeah. Maybe we could. So just this is really helpful. We want to come back to that. That's a key question. All these diseases. Maybe we could just briefly talk about the extracellular vesicles as a potential treatment modality for kidney disease. And we have sort of the same kind of questions, right?
Yeah.
Does it make sense? We gathered that you can sometimes administer these IV and they reach the kidney somehow.
So extracellular vesicles, emerging area of research, both in cancer and in kidney injury, and especially diabetic nephropathy. I know of specific people who are in this area as well. The thing is, I think it's a little premature now in terms of the biology and our understanding of extracellular vesicles. We can't even characterize them properly, except for size. We're not even sure about the markers. But so I would be a bit more cautious in jumping to this one too soon. But I think the attractiveness is that there's a natural system to absorb these things. So you don't have to work hard to get the thing because they exist. And also immunologically, I would imagine it's more inert compared to virus delivery because especially if you make it using cells that are in the body, then the exosomes or microparticles are more quote unquote natural than virus particles to deliver stuff. And they have a mechanism to get inside cells. I mean, cells are using this to communicate all the time. So I think and you can deliver anything inside them theoretically. You can deliver proteins. So it could be if you're deficient in a protein, you could deliver that. You can deliver DNA. You can deliver mRNA, RNA, and so that powerful. It's a powerful technology to deliver multiple things, and then you hide them basically inside these little vesicle-like particles. From the immune system as well. So I think it's going to be a lot easier to use. The problem is we need to understand the characteristics of the surface, what we call immunophenotyping or phenotyping these particles, so that because if you understand that, you can deliver it to certain cells and not other cells, because it's not like all microparticles or exosomes are the same. There are some properties that distinguish each type. And whether a dendritic cell picks it up or an epithelial picks it up. And I don't think we understand that very well. Maybe in a specific diseases, there's a bit more understanding. For example, just in kidney injury, for example, when you have ischemic kidney injury, and there's papers now in transplant literature where ischemic injury, which happens in all solid organ transplants, deceased donor, you get a rapid release of these exosomes. Now, some of these exosomes are coming from living cells, some of them are coming from dying cells, and they have for example, they can even trigger autoimmune responses. So they can be immunogenic in some instances. So we have to be careful not to deliver those kind of particles. I just feel like maybe there's still a lot of homework to be done before we start jumping to using this too soon. But it's an excellent way of delivering whatever you want to deliver. Better than viruses, in my opinion.
So, all right. So it's better delivery than viruses potentially. I mean, like you said, can you you mentioned a lot of things you can deliver with it. Can you deliver a monoclonal antibody?
To be honest, I am not aware of delivery of monoclonal antibody. I mean, theoretically, I suppose it's possible, but I am not aware of anybody using antibodies to deliver it. Now, what I can see, what people may do is, I'm not sure if you're aware of this CAR T cells, the CAR technology, which is basically attaching an antibody to whatever. In the case of T cells, we attach it to a T cell receptor, but you can target the exosomes using an antibody to an area. That you could do, but I'm not aware of delivering antibodies hidden inside exosomes. And why would you want to do that? Is the question? Are you trying to target it to certain areas or?
Well, I guess the question is, you know, if you can make the idea would be you can make potentially the antibody hit intracellular targets, right?
Oh, I see.
I assume if it's getting
I don't. I would not. I cannot think of a good reason to do that. I don't know if that'll be effective. I would rather use it for delivering small molecules, siRNA, miRNA, any of those things. I'm not interested. The problem with the antibodies is how they work. I mean, if you're using it strictly to block, and how they're going to be functional inside cells, I'm not aware of use of antibody intracellularly, and a lot of the effective functions of antibodies require the bloodstream or the complement and whatever else. So it would be not useful to deliver intracellularly.
Got it. All right, that's helpful. Thank you. All right, so I think we can switch over to the indications, but before I do, I just wanted to ask you. I mean, you know, I know this is early, but are you in terms of adeno-associated virus (AAVs)? Like, have you heard anything in meetings or other about different serotypes being, you know, better or less efficient at transducing kidney cells? AAV5 versus 2, etc.? I mean, anything come to mind?
The number 7 comes to, again, it might be some time ago, but the number 7 comes to mind. But I think that the higher numbers represent viruses that they've done more work on. But I don't recall, and I have heard numbers, but I don't recall specific numbers.